Everyone, thank you all for coming out to this momentous occasion. You all are here tonight to decide the future of the ACM, which is going to be a fun experience. Also, let me split these desktops so we can actually see the Discord. Everyone see me currently, perfectly in this viewpoint. The camera is stuck in position for some ungodly reason, so we're gonna have to give speeches sitting down. Okay, since I'm a good opponent, I'm gonna let my opponent go first in the speech category. No, you can go ahead. I don't mind. I'm not trying to fake you out by making you nervous.
No, I'm just
you may go
starting
first.
speeches.
Okay, well, I guess I better go first for the presidency. Okay, hi everyone. If you don't know my name, then where have you been for the past several years? Okay, long story short, my name is Alexander N. DePaulo, Nick DePaulo as most people know me. I have been a CSE student here for the past, just about 3 years, ever since 2019. Feels like 10 since 2020, but I digress. I have been really excited for the longest time to take a leadership position, especially in the ACM. When I first came to here, I was extremely excited to just be able to get membership committee chairman position. I'm very grateful that Kyle appointed me in that position. But I want to do a little bit more with the ACM. I care a lot about this little computer club we got, and I want to really evolve it into something that we can all appreciate. I want to get it to a point where future generations who come into the program are able to manage this with ease and do really cool stuff. Like, for example, some stuff I really want to do is one thing I want to do is a lock-in, or even maybe one day host our own hackathon, which would be really cool. Actually have sponsors and stuff like that come here to do challenges and things like that we put forth. I think that would be a really cool, that's a bit of a grandiose scheme, but I'd like to get things in the works to one day reach that point. But currently I want to keep putting my all into this program. First thing I want to do is start a pizza fund. That's especially is what I want to do, because I can't keep growing, what am I saying? I can't keep growing broke providing pizza for everyone that is here, even though I'm very thankful for all you guys just attending all the game nights I've set up and all the crazy stuff like that. So I want to keep up this momentum we got going, and I want to be able to get participation up a lot. I want to also start doing workshops and stuff like that. Something really cool that actually my opponent, quote unquote, my fellow candidate, Brian, suggested was trips to Hollow Weekend or trips to museums and stuff, which I think would be a really, really cool idea. Being able to organize museum meets and things like that would just be an all-around really cool idea. And I think this little chapter we got can really grow into something really cool, and I want to be able to do that. So, and I hope you will allow me the chance to be able to do that. All right, thank you. I think that's all I need to say. You're all beautiful. And something else, I don't know, whatever. All right, now to my opponent, Brian Angel. Angel, I'm so sorry. Oh,
it's okay.
My God. They're going to use that in a scandal against me. The opponent's name wrong. No, get down. Fuck the camera. Oh, go ahead.
Hi, so if any of you don't recognize me, I'm Brian, actually pronounced Angel. I go by B though, no big deal either way. In case you don't recognize me, I'm actually a junior in the program. I never really hanged out in the Sun Lab while I've been here. Since the summer, I've been on co-op though. I kind of realized a month or two ago that I kind of wanted to be more involved, more active in the college, kind of less separated from everyone. I started attending ACM meetings, and it just kind of corresponded with the same time where the election kind of started ramping up, or the idea of one, at least. Kind of as Nick mentioned, I've kind of been an ideas guy. It's kind of the two of us have been in contact on Discord, just kind of talking about different stuff that we could potentially work on. I actually kind of have a list of kind of some of the things I've been thinking of. I'm big on feedback. I don't want to like force anything to happen that's not really kind of working or nobody really thinks is a good idea, kind of killing the mood, if you will. But just like some of the things that we've been talking about, like Nick mentioned, like going to museums, kind of field trip style meetings. But I don't want to limit it just to museums. I'd like to at least aim bigger if possible. Some of the things that I've written down, like the NASA Glenn Center, where Professor Nolan works at, I think it'd be really cool if we could organize like a tour of that building. And I think they actually do have tours to the normal public.
To the normal public places that you can go to. So
yeah,
we can try and get Professor Nolan to sneak us in the back door.
Yeah, I'm not certain how hard it would be to arrange like a group to go in, but they do.
No, they allow public in certain places that you can actually go and tour. From what I remember looking at.
Okay.
But I'll have to double check it.
But we can look into that, but that's a potential idea. We've also talked about like landmarks, or a big one that I would like is there's a air museum. I've mentioned a few times I like planes. Another idea is like I call them challenge nights. I think you called them.
I called them. I think.
Nick had a name for it.
Similar to what like a mini hackathon to like you stay up and you like but it's like centralized. Like it's just for the CSE people and that sort of thing. And never mind, I'm sorry, that was just Seth saying something. Go ahead.
Just so some of the ideas I've had is like an egg drop where like you kind of build whatever to protect the egg, and we kind of each build something, and then whoever can survive an egg from the highest height, or like jumping robots, or...
Ooh, you know what would be cool is like an Arduino, because Arduinos are relatively, depends on the board you get, but it'd be really cool to do.
We're getting off track.
Okay, I'm sorry, go ahead. I'm interrupting your speech. You're making me get more cool ideas.
Nick's getting excited. I've also thought about like model rockets, having like a little rocket chute, or I know Science Olympiad has a whole bunch of little projects that we could kind of look into, just to kind of change up the routine of lectures, game nights. Nick added in a movie night, but I think adding in some variety could help with participation, which I'm big into. I want more people to be involved. But with that being said, I don't want to eliminate lectures. I think that's a good way to keep remote participation and to just have everyone have their own kind of personality show in the ACM club itself.
I think the biggest thing we want to try also do is maybe get some freshmen actually to lecture, because that'd be kind of cool.
Yeah.
Because one thing, the highest way you can actually learn something is by teaching someone else it. Oh, it'd be awesome to reinforce people's knowledge by actually having them come in and give lectures to their fellow peers. So, I'm interrupting your. I'm sorry.
No, you're fine. Just having freshmen get involved in lectures, but also like the challenge nights that I was talking about, like being active is a good way to learn, and it's also a lot more fun. Not that lectures aren't fun, just like it's fun to be involved and actually, hey, I made this thing, and I learned something while doing it. It's just applying knowledge. I think that's just the main focus that I have, is keeping it educational, but having fun to increase participation. That's kind of the goal that I have when I think about running. That's all I got.
I think that's it. All right. Thank you to everyone. Oh, and Joey, I didn't miss your little Discord message. You said we still have those Raspberry Pis?
Nobody took them. We left them. I think they're in like one of the drawers in a Sun Lab somewhere. So
I've definitely seen one floating around the Sun Lab.
This is perfect. That would be actually a really cool idea. Time to bust those out and start tinkering on them. How many do we have? Aren't there like
we
3?
won 3, but I don't think any of them came with SD cards or anything. Like it was literally just 3 boards.
With Raspberry Pis, they're like a.
You should be. Go ahead. Oh.
With Raspberry Pis, they're a little higher up on the operating system compared to like Arduinos and using ESP32s. But like, just a thought is you can get ESP32s for like $3 a piece. So, like if that's something that we need, like they're not expensive, and there's so many things you can do with them. Like,
Yeah, it'd be cool to have, like you said, a challenge night where like you have like the entire night until morning and like it'd be like the winner gets like a $50 gift card to Starbucks or something like that, like where it's worth it, but not like where we go broke to the point of prize pooling.
they don't all have to go all night.
Yeah, they all
It
don't.
could just be like a quick.
Yeah, like you
couple
have
hours.
2 hours. Like we'd probably do something a little shorter. Like you'd already have like the board set up and it'd just be like code it to flash these lights at this time, and you'll have a few freshmen participating and stuff like that, which would be really cool. Yeah. So we can even do it as like an interactive lecture for people who are here. And I know it might kind of
that we could use
yeah, definitely.
for
That'd be really
remote
cool.
is to use emulators.
Yeah, so we get that set up and we ask people, okay, here's what you need to download for the upcoming lecture and such and such. So it might be a cool idea.
You don't even have to download anything. They're like web-based ones.
Oh, nice.
I think advantage of all sorts of like Arduino and
That's how I got mine out.
actually.
Nice.
I
You
did
think
a
you're cat?
little thing on the webpage and I just saved it, back.
I'm sorry, got stuck on student camera for a moment. I didn't mean to interrupt you. Okay, awesome. All right, we're going to go ahead and transfer then control over to Joey. Thank you all for watching this little, quote-unquote debate. We will be posting later on after the ACM meeting for tonight ends. We will be posting the voting. Like I said, we will be only voting on vice president and president, treasurer, and membership committee chairman. Membership committee chairman is always appointed, but for this one specific time, we're going to have to appoint a treasurer because we had a bit of a lack of people signing up for the sheet. Come on, guys. No, I'm kidding. But yeah. So it's going to act a little differently. So like I said, the 2 candidates are me and Brian. So we'll be setting up the sheet later tonight. So awesome. All right. Thank you, guys. Now it's time, ladies and gentlemen, the moment you've all been waiting for the legendary Joey Kilgore. I don't want to get too crazy. Like Joey, Joey's awesome. So you guys are going to have such a treat. I mean, half of the people here already know this man's name by heart. So, all right, Joey, I'm going to go ahead and end this stream, and I'm going to let you take over and bring us through the wild ride that is robotics.
Awesome. Okay, I think I started it. For some reason, like 2 minutes ago, Discord completely closed for me. So, and the other thing is my mic is almost always really quiet for people. So if it's too quiet, you guys can yell at me and I can turn it up. But I think most people have to crank me to 200% on Discord. So hopefully it's okay.
Yeah, we're good on the volume thing because we can turn up the room volume thing. So we're good.
Okay, and you can see my screen and everything?
Yep, we can see the slides. You should be good.
Awesome. Well, thank you for probably what will be the most emphatic introduction I'll have for my entire career. So if you don't know me, I'm Joey. I'm a second-year PhD student here at George Washington University, which is in Washington, D.C. I graduated from University of Toledo in 2021. Yeah, that's how math works. And currently I'm studying, so it's a PhD in computer engineering. That's the program I'm currently in. And I'm focusing on biologically inspired artificial intelligence. But what I wanted to talk about today, I kind of wanted to go with kind of a funny title to try and get at the point I'm trying to make, which is The title of this talk is going to be Artificial Intelligence Opening Up the Buzzword Blackbox of Backpropagation and Convolutional Neural Networks and Multilayer Perceptrons, because I feel like in technology, we throw around a lot of buzzwords and we've kind of lost the meaning to a lot of them. And so the hope of this is to try and not to have you understand every single buzzword, but to at least show you them. And then throughout this presentation, I've filled it with links. And at the end of it, I literally have an entire slide of things I didn't cover with just links to a whole bunch of stuff, and tried to give you as many resources. So I'll send a link to these slides after, and that way you can just have it for a reference. So whenever you need to look up some weird AI term, you can go back and be like, oh yeah, this presentation had a whole bunch of links to stuff. And hopefully it'll be kind of more of like a helpful document as opposed to this just being a lecture that you sit and listen to.
Thank you, Joey. Sounds good. And if there's any questions, I'll let you know if there are any in the chat or any in person here, okay?
Awesome. Thank you so much. Feel free to just like interrupt me too.
No problem. You're good. Go ahead.
Okay. So kind of continuing off this idea of what this presentation is about is the idea of we have all these buzzwords, but what do they like actually mean? And so to go through this, I'm going to start by talking about just like the basic two terms, which in this case, I'm just going to look at artificial intelligence and machine learning. And then we're going to kind of start from what are the building blocks of like traditional machine learning algorithms and kind of step it up to how do we train them, and then how do we implement them. And then I go through like a brief little case study at the end of how we can think about how we actually use artificial intelligence and machine learning in the real. So that's kind of the hope and direction of this presentation. So to start off, artificial intelligence and machine learning. I don't know if you can see, I wish I could have like is there a laser pointer? Yes. Okay. Can you guys see my laser pointer?
Yep.
I can see it.
Awesome. Okay. So the artificial intelligence, so these are both just the definitions. I think I scraped them from probably just from Google. But the main difference here, so artificial intelligence is the theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, translation between languages, etc. The key point of artificial intelligence is it's performing a task that normally requires human intelligence. That's the key for artificial intelligence. And we kind of just throw that around because a lot of times when we talk about, robots doing human-like things, that's because it actually is under the definition of artificial intelligence. The other word we throw around a lot is the word machine learning, which is actually a more specific term. So it's the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms and statistical models and stuff that we'll talk about later. But pretty much every instance of machine learning is like a specific form of artificial intelligence, because usually you're learning and adapting to perform some complex task. So hopefully that kind of makes sense. So when you hear people just throwing around the term machine learning and they're not actually doing any learning and adapting of the algorithms, then it's not actually machine learning. It might be artificial intelligence, but it won't be machine learning. So that's kind of an initial kind of taste of what this talk is pretty much going to be, which is just a bunch of buzzwords and me kind of giving you just a little taste on how they're nuanced. But hopefully this makes sense.
Sorry, Joey. Am I going to have to clickbait the video when I upload it on YouTube?
You are more than happy to clickbait all of this.
Okay, continue.
Thank you so much. So the building block of machine learning is known as the perceptron. And it looks kind of complicated, but it's really not. What happens is, if you kind of taken like maybe the nonlinear data structures course, or even if you can just follow arrows, hopefully, you start off with inputs. These will be typically values from 0 to 1. They don't have to be, but most of the time that's kind of traditional way to conceptualize it. They get multiplied by some weight and then summed together. So this input will get multiplied by some weight, and then it's added together, and then we throw it through some step function. And this is kind of the building block for how we get neural networks and how we get all the other things in machine learning, which is this fundamental idea is loosely based on how your brain works. As somebody who actually has like tried to study how your brain works, your brain is a whole lot more complicated than this. This is like an extreme simplification that was actually done back in, I think it's around the 60s, because we didn't have the computing power back then to be able to handle what your brain does. We don't really have it now. Well, kind of. It's complicated now. It's a question now. It wasn't even a question back then on whether we had the computational ability. So, but what we have here is this kind of idea of in your brain, you have neurons that fire and send information. It's kind of what it's trying to do here, but doing it in a way that makes math a lot simpler. But so it's this idea of we have inputs, they go through a weight, and they get summed together to give us an output. And then that output could be an input to the next perceptron, right? So this idea of a perceptron is maybe why you might have heard the term multilayer perceptron, which we'll get to in a sec. But I think it was also nice to just include a little example. So we have inputs, right? They get multiplied by some weight, and then I added them together. So in this case, I actually went and did the math. So if you do 0.4 times 1.3 plus 0.7 times negative 2.3 plus 0.5 times 0.2, you get this 0.99. And then what you would do is you would take that 0.99, pass it through some activation function, and get an output. And I left a reference for this at the end. There's a whole bunch of these different activation functions, and I'm not going to really cover that. It's kind of more, here's another term to throw at you. But this idea of multiplying, summing, activating, and then passing it to the next thing is the fundamental piece of a neural network in machine learning. So hopefully, like, just even if you don't understand why the heck we're doing this, you can at least understand that, okay, I know how to draw circles with arrows that connect to each other, and that it kind of makes sense of how to do math. So that's kind of the hope. We can then put them together into what we call a multi-layer perceptron. I think that it makes sense because it's like multiple layers of perceptrons, right? Because it's the same idea of all of these are inputs to this. They get summed together and then put through an activation function. And then each of these are the inputs to the next one, right? It's like a really straightforward idea. I don't particularly like the term multi-layer perceptron. I think it's it's complicated until you've gone through all the beginning process, because a lot of times when we see this word, it's just called a neural network. And that's kind of the term I kind of prefer to use, because people immediately know that, even if they don't understand all of the background. And so this kind of makes it, unfortunately, it is kind of also one of the buzzwords where people don't actually necessarily know what it means. So it's kind of the double-edged sword. But so that is the fundamentals of how a neural network works, essentially. So you have all of these little summation things that go on. You have multiplication, summation, activation, rinse and repeat, rinse and repeat, rinse and repeat, rinse and repeat, rinse and repeat. And that's how a neural network works. Are there any questions on that so far? I love awkward pauses.
No questions.
Okay. To kind of expand the convolutional network, to kind of really push your understanding of it, we have push your understanding of multi-layer perceptrons. We have convolutional neural networks, which instead of it just being like a row of values that we feed into the next row, it's an image. So if you took the idea of a neural network, but instead of one-dimensional, you made it two-dimensional, you would essentially be doing what a convolutional neural network does. Where we have a two-dimensional network, we're going to have a two-dimensional thing of weights that get multiplied and summed together, and then that gives us one pixel in the next layer. And then all of these images, I'm going to use the term image loosely, because it doesn't really look like an image anymore at this point. It looks kind of just like a collection of pixels. You do the same thing. You take a group of that, you do weights, you multiply by weights, you sum them together, and you put them in an activation function to get a pixel in the next layer. And you continue that and continue that and continue that. And you can see, like, this shows you one set of connections to a single pixel on a single one of these frames or feature maps. Every single pixel on every single one of these feature maps has some set of connections that go back to the previous. And why is that important? It's because the weights, I think it's on the next slide, each weight is a parameter that we can adjust. So when we go back, I'm going to go right back to the same thing we started here. We can't really change our inputs, right? Because that might be some physical value we're getting. Like if this is predicting whether or not it's going to rain tomorrow, it could be temperature, humidity, and I don't know, time of the year, right? And they're put into some 0 to 1 scale. These weights are we can't change the humidity. Well, not yet. But we can change how our network accounts for it with these weights. That's kind of the idea of calling them like a parameter. There's something we can control. And so when we think about these later networks, and this is another example, all of these connections are things we can tune to try and get our network to do whatever the heck we're trying to get it to do. So then the question is, how do we train them? I'm going to use well, first off, before I explain anything about backpropagation, which is kind of one of the traditional ways we do math to solve it, everything I'm about to say is almost a disservice to you. You're better off to just like turn this off and go watch this video, probably. I'm going to cover other stuff beyond this, but this video by 3 Blue 1 Brown, it's a 4-video series, is probably one of his animations are absolutely amazing, and his explanation of all the math is absolutely perfect. Like, it's so easy to follow through. So if you're ever interested in understanding the math, I'm kind of going to blow through and just give you the high-level idea. If you're ever interested in understanding it any deeper, this video series is probably the absolute best thing you could watch or read about to understand it. So that's my kind of disclaimer before me trying to talk about it in any stretch of the imagination. So when we look at the network, I've kind of simplified it down as a single neuron in each layer, right? A single node in each layer, and then they're feeding through. So what happens is if I have a value of 0.4, it will get multiplied by this, summed together with if there were any other ones, and then pass through an activation function. And then this gets multiplied by the 1.3, pass through an activation function, we get the 0.67. And the same thing here. So that's the propagating forward, which we already kind of talked about with the perceptron. But what we can do is take this output and compare it to some value that we would expect. If we gave it the value of 0.4, we expect something else, and we calculate some loss value based on that. There's a bunch of math that goes behind this, and I didn't want to just cover a slide in equations of partial derivatives and stuff like that. But that's something you can look up on your own. The idea is just that we give it input, it gives us output, and we can calculate some loss value from it, some error, right? This could also be just error. From that, we can calculate the partial derivatives of each component relative to that loss. And that was a really complicated thing to say. So let me kind of step through it a little bit. We can take this loss function. The loss is a function of what? It's a function of the output and what it should be, right? Well, we can calculate then, because it's a function, the partial derivative of the loss function with respect to this node. So we can calculate the partial derivative of the loss function with respect to this node. The partial derivative being the gradient. Those are synonymous in this sense, where this value tells us how much changing this. So the gradient value tells us how much changing the value of our function will affect the loss. And it actually will inform us of how to change the network. Now, obviously, we can't directly change the value of our nodes, right? But we can change our weights. And so we can use the chain rule, right? Because we're thinking about partial derivatives. We're thinking about derivatives. We can chain backwards through the network to all of the different components of our of the network, the weights and the nodes. And you could do it through the whole network. And through a more complicated network, you do the same thing. You look at the whole output, and you can use the chain rule, because this is all derivatives, back through the network. It's kind of scary to think about. And I recommend going back to the 3 blue 1 brown video. He does this much better than I ever could. But this idea of this gradient tells us how much changing the weight will change the loss. And if this tells us how we can make the loss be less, right? Because we want to minimize loss, right? We want this output to be exactly whatever we're trying to expect. And if it is what we would expect, the loss would be 0. So if we can minimize this loss function, then we're good. And if we can change our weight to reduce this loss, then that's also a really good thing to do. So all of this, there's all this math under the hood that I'm not going to go through. All of it basically points towards this idea, which I'm going to make sure you're all kind of getting this last point, which is the fundamental idea of backpropagation is to update these weights such that the loss value goes down. In other words, we're updating these weights based on a bunch of complicated math so that the output is what we expect, right? Because that's the same thing as saying minimizing the loss, is saying the output is what we expect. So that is backpropagation. It's called backpropagation because to do all those partial derivatives and stuff, we'd use the chain rule going backwards through the network. But this is one of the fundamental things of using math to optimize our machine learning, or optimize our neural network is probably better things. So I realized that was probably very painful to listen to. So are there any questions on that?
No, none from you, Nate? I do not.
I got the partial derivative.
Okay, yeah, we helped him out. We helped him figure out what, because he's a freshman, so he's going through Calc 1, so we kind of had to put back together his brain with a few screws.
Okay, yeah. Don't worry about this till Calc 3.
So, continue. You're good, Joe.
Awesome.
So I guess I have a question about when you were talking about parameters and parameters being essentially the edges between the vertices. When people say stuff like GPT-3 has however many billions of parameters, are they referring to those edges between the nodes?
Yes. But I'm going to give a caveat of, I think that, but their network structure is also a lot more complicated and nuanced. So there are other things that they might consider parameters. What he's talking about here, I was able to find it. OpenAI, so GPT-3, which I don't know if I mentioned it later in the slides, but it's a language processing model. And it has 175 billion parameters. So if you think about this has 3, okay? And hold on. I didn't mean to go that slide. This one has 25, okay? And to think about what it would look like to try and draw out what 175 billion is. We also have to think about all of the computing power to just, like, first off, the computing power necessary to hold all of that information is astonishing. The amount of computing power to then calculate, right, I can't remember exactly what they used to train it. But if you were to do, like, have a neural network, traditional one, with 175 billion parameters and then do backpropagation on it, you'd have to go backwards through 175 billion different things. And when you get to billions, I think that correlates to like giga in terms of like processing when we think about like gigabytes and gigahertz. So it's kind of crazy to think about the scale when you look at that. But yeah, so these would be considered our parameters. That's kind of why I tried to use that term. They might have other parameters that they use. So sometimes you can include, I don't know if I have it in the slides here, but you can include like an extra bubble at the bottom that's just always 1, and that'll be called a bias. And sometimes you can add that as well as like another parameter. It's basically just like an input that's always 1, just to feed it into a network. And that can be helpful.
Another fun thing about GPT-3 is that it wrote a poem about the geese at UPRC.
I forgot about that one. Awesome. Are there any other questions on this?
Good.
Awesome. And I'm going to go to Brendan's favorite, the NEAT algorithm. I don't know if it's actually his favorite. I just know he tried to use it, or did use it. Tried. Instead of using math, we can let Darwin do the work. I just kind of included this to show the idea that there are tons of different ways to train a network. There's things like Q-learning, which is really complicated. At least it's complicated for me. There's this NEAT algorithm. There's there's backpropagation, and there's a whole bunch of variants on backpropagation. There's a ton of different ways to train your network. I'm just showing you these ones as just like, here's some basic ones so that you can like see that there's different ways to do it. There's not one, this is how we train our neural networks. It's not like that. It's more complicated and nuanced, and everybody kind of has their own little thing. And one of the parts of that is that everybody kind of can do their own little thing, and you can tailor it to whatever your particular situation is to find out whatever the heck works best for your situation. In this, the Neural Evolution Augmented Topology, or NEAT algorithm, basically it sets it up to be like this Darwin-esque survival of the fittest, where we randomly make networks. In this case, they're not nice and feed forward. They're like these complicated things. But oftentimes you still use that kind of perceptron idea of sum and add, and then pass through a activation function. But in this case, the network structure is a lot more complicated, right? And then what we can do is add connections. In this case, you can mutate things by adding nodes. And then what you can also do is take two different networks and then combine them together. And the idea being that, like, essentially, you create a bunch of random networks. It's the idea of Darwin survival of the fittest. We create a bunch of random ones. We see who does the best, and we let the best ones mate to create the next generation. And then we add in a couple random variations to see if we can get something new, right? And then we let it run again. And we take the best ones and mate them together to create new networks. And then we add some random variations to see if we can pop out something new. And then we test them all again, and then we let the best one, and you just kind of let it go over and over until it like gets to some like best point. This one, I honestly just personally just enjoy the idea of just letting it figure itself out, because the math one, it's designed by math to give us statistically point towards a local optimum. I'm not going to explain all the math under that, but that's just what it does. It goes towards a local optimum of the parameters. But the NEAT just kind of randomly goes and finds out what it could do. And I think that's quite, it's just kind of entertaining how different of a perspective that is. And there's some other methods for training that go in a completely more math-oriented direction. And I think there might be others that kind of just stay in this realm of like random chance and seeing what happens. Typically, this random chance one is kind of, it's not used as much in like industry scenarios, because oftentimes they want to know the math is going to lead to something. This doesn't inherently state that it's going to lead to the optimum solution or an optimum solution. So there's kind of like a little back and forth with this. I don't think these are typically used as much as the kind of more straightforward math-oriented algorithms. So, but I thought this one was fun to include. There's also a bunch of videos you can look up of like AIs, like I think Code Bullet makes a bunch of videos of him like controlling video games with this kind of like evolutionary AI or evolutionary machine learning. And so it's kind of entertaining to watch it like evolve and go from being one thing to then improving on itself and stuff. So just kind of as like a side thing.
Is that what Mar.io is, or is that something different?
Yes, Mar.io. Is Mar.io still alive? No, they canceled it and went to Luigi.io a long time ago. And I don't know if Luigi.io is still running. I think it beat, oh my goodness. So what we're talking about is somebody had made an AI that plays it. And so in this top corner, you can see it takes the map of the screen, and then it's the network that gets changed around that then goes to button outputs. And then it plays the game, I think, on this screen then. And then they have like the map of how far it's gotten into the level. Like this is like the mini map of how far it gets. And then this is like how many days it's been going and stuff. It's crazy. And then the generation is like, what's the, iteration of us testing all of them and then playing it again. And then was the species genome and stuff like that. So they kind of, this project, like if you look at it from the beginning, it did not have like this crazy amount of stuff on it, but it's really entertaining to see this as like a fun, kind of interesting way to observe what these networks are capable of, just on the idea of, in some sense, random chance. But yeah, Luigi.io and Mar.io, quite entertaining.
Moved on to the superior Mario brother.
Yeah, I'm still waiting for War.io. I think they wanted to try and play the WarioWare games, which I think would just be crazy to watch.
Oh, cool. That'd be a wiggly cool. I'd love to see that.
Well, so we could use Mario games as a data set. Or we could also use, I'm kind of using these, this is particularly like a supervised learning kind of data set oriented idea. But there are a bunch of other different, so there's supervised learning, semi-supervised learning, unsupervised learning, reinforcement learning, and I have links to them at the end if you're interested in understanding more about that. But kind of the key things, I kind of just grabbed a couple of like the immediate ones I could grab off the top of my head that people use a lot. There's the MNIST data set, which is probably one of the hallmarks of data sets in machine learning. It's just 60,000 handwritten characters that have been checked to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we see how well a machine can get at predicting it. There's ImageNet, which I think has like some 100 millions of images that are then categorized by like a series of different categories. If you remember, kind of these images might look semi-similar. If you remember having to do the CAPTCHA, where you had to click on an image, you might kind of notice some similarities there, question mark, of maybe we used it to train AI, question mark. So you can think about that. You have Fashion MNIST, which is basically MNIST but clothes. I still don't fully understand the difference between t-shirt and there's some other one that's like really similar to t-shirt. I don't know. But it's basically the same idea of 10 categories of clothes. A lot of times I like to see when they do like textual stuff, they'll grab things from Wikipedia or Twitter or Reddit or a bunch of other stuff. So that's always kind of funny. And sometimes like specific people like Elon Musk and Donald Trump have like their own, people have specifically gone out to scrape their tweets and put it together in a nice data set, which is always entertaining. And a lot of times also economic data, whether that's index funds, individual stocks, mutual funds, it doesn't really matter. Currencies, if we can figure out how to predict it, then there's money at stake. And if there's money at stake, then people are willing to work on it. So that's kind of where that one goes. And obviously there's tons more that, like this to say this is scratching the surface is really a lie. If you go to, let's see if I can go to Kaggle.com. Yeah. Data sets. Great. So this is a website for people to post data sets. These were posted, 3 days ago, 6 days ago, 4 days ago, 3 days ago. Like, there's just so much. 174,000 data sets. So if that's not enough data for you, I don't know what is. Now, some of these are just like random ones that people have made on their own. Some of them, they scrape public APIs. So like you can scrape Reddit, you could scrape Netflix, you can scrape a bunch of other stuff, Tesla, whatever. And then just post it is what a lot of people did. But so Kaggle.com, really good. I don't know if any of these links go there, but all of these go to whatever the data set is. So. One thing I just want to kind of make a point, because this is brought up a lot when we talk about how do we train and test it in terms of the data set, is we break up the data set into a training set and a testing set. And the reason for this is because the training set, we're passing it to the network and we'll do that like backpropagation math, and we'll do all this stuff so that theoretically it's supposed to be able to figure this out if we give it enough time. To like be able to do this 100%, theoretically, is the idea. But the testing set, we don't show it and we don't let it like work on it, because that way it's like it's a new thing that it hasn't seen before. So that way we can run through all the training examples and then do our weight updates, update our parameters, and then test it. How well did we do? Is it doing good? No. So we'll run it again. We'll run it on the training set again and then test it again. And this idea means that we can check whether or not it's like actually learning what's going on here. Because if we can show it examples that it's never seen before, then that means we're on the right track, right? And so with that comes this idea of fitting and overfitting and underfitting and generalization, which is this idea of, I kind of mentioned the training set, you should always be minimizing the error throughout training, right? And I included this as another kind of buzzword on this slide of epochs. An epoch is just an entire iteration through the training set. So on the MNIST data set, it's 50,000 training examples and then 10,000 validation or testing samples, right? And so theoretically, if we're training on it, we should always be improving our error, right? The error should be going down, right? Because we're giving it to it and we're saying, do math to optimize for the training set. The problem is, as we do that, for a time, we should also be getting better at the testing set, right? Because at the beginning, it should be like, this is what a 3 looks like. This is what a 4 looks like. This is what a 5 looks like. And so it gets generally better. And so we see improvement on our validation set as well. But there is a point where we actually kind of stop learning about the general, what is a 3? And we start learning, what are these specific 3s, right? We stop looking at the whole edges and we start realizing like, oh, these 3s have like this one particular pixel, that's black when nothing else is. So I know if I see that pixel, then I know it's a 3. And that might not be true for the testing set. It's those kind of like, it starts being less about generalizing and it starts overfitting to the data set. That's what that term is. We're getting too specific on that training data. And that's why we keep the testing data separate. It's so that we can check when it starts to do that. Because imagine if we just fed it all the data we have, right? We would never know when it starts to just pick up on all the stupid nuances in our data that aren't actually what we're trying to get it to do. So that's kind of the idea of looking at data sets. And I want to make sure I don't think I have any other slides. So are there any comments, thoughts, or questions on data sets in machine learning?
Stop computers from trying to forge my signature.
We'll get to that.
No questions currently, right? Nate, do you have any questions? No, I'm good. Okay, I think we're good. I think going ahead and continue. You're good.
Okay, so now we're kind of going to take that next step back of how are we using these. We have natural language processing, which oftentimes is abbreviated as NLP. Optical character recognition, oftentimes abbreviated as OCR. Optical character recognition is essentially what the MNIST data set is, which is look at handwritten characters and tell what it actually is. It's kind of easy when you start with the numbers 0 through 9. It gets a little more complicated when you start adding letters, and then it gets more complicated when you're doing Arabic. So there's that problem. Speech recognition, which is basically what the personal assistant that shall not be named would be doing. We have speech segmentation, which is being able to tell when somebody's like talking, stuff like that. Text to speech, which hopefully is obvious. Sentiment analysis is taking text and then deciding whether or not it's like a positive or negative thing. So oftentimes it's used with like comments on Twitter or YouTube or various other things like that. You can then use that idea to see whether somebody's talking positively or negatively about something. There's text generation, like using GPT-3 to make a poem about the geese at UPRC. There's translation, so between languages, right? Like Google Translate. We have facial recognition, which is being able to have a camera pointed at it and connected to a database, and it'll be able to look at somebody's side of their face until it matches, their picture in their database or whatever it is. Object detection, which is being able to have a camera and tell when there's an object in a frame, and then object classification, which is telling what kind of object that is, because those are two different tasks. And a lot of times, like tasks that we think about as like one thing in our brain can be broken up into a whole bunch of different things for a computer to have to do. And then there's like forecasting, which is like looking at the economic data. And there's a whole bunch more uses of machine learning. Like this is barely scratching the surface. Again, this isn't about me trying to give you every single thing. It's here's a bunch of things. Go ahead and look up more. But with that comes some questions about AI as a whole. So we started off by talking about what machine learning and what AI is. And then we went to talking about kind of the building blocks, the fundamental, the perceptron. We moved up to neural networks. We moved up to training those neural networks. We moved up to how we would implement that neural network and what tasks we would use it on. But then we have to take a step back and look at the whole process and make sure there aren't problems with it. And one of the fundamental problems is this idea of the black box. And the idea is that we don't know what the network is thinking, right? Because you and me, we say, oh, this is a 0 because it's like a circle and there's nothing in it. So that's a 0. It's a 6 because it's like a circle with like a tail. So that's why we call it a 6. But if the tail is on the right side and going down, then it's a 9, right? And we can explain that. But the neural network can't explain anything, right? So the problem we have is, how is it thinking? The other question is, if I feed the network like 100,000 zeros and then like 100 ones, and it gets really good at figuring out zeros, but basically can't figure out what a 1 is that a problem of the neural network? Probably not, because it's really a problem of the data set we're feeding it, if it's biased towards one thing or another. And just as an example that's maybe somewhat important, especially since there's a lot of questions on facial detection right now, I think certain states have like outlawed the use of facial detection in like camera systems and stuff, because there are certain problems with it. One of them being, I thought that this was an interesting statistic to pull on the skin color and their ability to recognize it in facial recognition systems, right? And like, I don't know if I can call a neural network racist, right? That term doesn't really make sense because it's not thinking about anything. It's just biased in its math, right? And so when we think about this and the fact that we really don't understand what's going on under the hood is really problematic in some situations. Now, when we're guessing stock prices, we might as well just be gambling. So we might as well just go with whatever random number pops out and says, go bet on Tesla. Sure, why not? And maybe when we're doing pricing modeling and stuff like that, or predicting the weather, it's not that important. Maybe it's slightly more biased to it being rainy today. But that's not like the end of the world. But then if we start implementing this using this to detect like shoplifting and things like that, where you can easily see this being applied. And this was actually, they used facial detection to figure out some of the people who were in the Capitol riots on January 6th. You start to have some questions about how important it is to understanding what's happening under here. So I just kind of wanted to bring this to light as kind of, yes, it's an amazing tool, but it isn't perfect, and we need to acknowledge that. So sorry to bring down the mood, but it's kind of important to focus on this. And to keep bringing down the mood a little bit, I'm going to jump right into autonomous weapons as well, and understanding that there are questions with using AI, right, and using machine learning, because we don't necessarily understand what it's doing. If you're interested in understanding about autonomous weapons, this book is absolutely amazing. I can't remember. I think Paul Scher, let me make sure. I know he worked as part of the, let me see if I can find it, Center for New American Security. And I'm trying to remember what his full title was. So he's the Vice President and Director of Studies at CNAS. And I thought, he previously worked in the Office of the Secretary of Defense and played a leading role in establishing unmanned and autonomous systems. So he's very knowledgeable. It's an excellent book. And I think one of the questions we have when we start having autonomous weapons is autonomous weapons are better than human-controlled weapons. And so then we have to question, well, do we give the autonomous thing that we don't understand how it works the power to just lay waste to large quantities of people? And that's a concerning question to ask. And so it's worth considering what we're doing while we're doing it. So are there any questions on, I think there's also, I did a talk on AI ethics, just kind of a brief overview, and I think I stole this slide from that. So are there any questions on this so far? I see there's 2 questions in the chat. Do pre-trained neural networks simply already have the weights already adjusted? So yeah, so a lot of times what they'll do, I'm going the wrong way. You'll have a network like this, and they'll pre-train a bunch of it. And then what it'll probably do is it won't be like an output of what you're asking for. And then they'll add like an extra bit of network to connect it to whatever you want to do. So it'll be pre-trained to like, a lot of times like it'll be like text encoding. So it'll kind of understand the sentiment of whatever the text is. And then you're like trying to figure out some further thing on it. And then you can like attach a piece on the end and then train that last little bit. So this beginning part will be really good at like disseminating the information from something. And then your part will just do whatever that last little bit that you want to do is, if that makes sense. Is there any more training involved to take the pre-trained network and adjust it to the application? Which is basically that idea of we'd add maybe a couple more layers, because it's not necessarily one output. It might be like 100 million outputs. And then we connect that to maybe a couple more layers, and we'll train those additional layers to whatever particular application is what would normally happen. So hopefully that makes sense. Okay, to finish this out, I wanted to go through like a case study on how you can think about the use of machine learning and AI. And one of the easiest ones and kind of immediate one of why is it important? We can think about like fraud detection, especially in banks. Like it's kind of like there's an importance to this one, right? I don't want people stealing money out of my bank account, and I don't want to be able to make fraud transactions for other people and have it just go through. That doesn't seem like a good idea. And we can set up rules where it's like if you go out of the country, then it gets automatically flagged or things like that. But it's hard to just set up a bunch of rules to define every case of what we think fraud is. It's kind of hard. And so the question is, could we try and use machine learning to predict? And prediction is a really key thing that machine learning is good at. So the first step is data collection. And this is kind of like, you kind of think, well, like, duh, but it's a really important part because it is going to define how well you can do for the entire rest of the project. So you need to get data, and a lot of it. Like I said, MNIST is like 60,000 samples. Obviously, if you're like a major bank, this isn't a hard thing to get. But getting it, putting it, and making sure it's classified, whether it's a real transaction or a fake transaction. Hopefully there's a bunch of real transactions, and hopefully there's a bunch of fake transactions. And then putting it in a manageable format, because we're going to need to work with it. And this will be called like data wrangling or something like that, or data formatting, or various other terms that people have for it. This is where like a lot of work can go, because you might be getting like, oh, well, like part of our company uses this format and another part of our company uses this other format. And actually this like third department uses its own format that's actually completely different from these other two. And you have to figure out how to put it all together. Can be very challenging. And then cleaning it so that you remove like, oh, like occasionally it'll just like have a random transaction with $0 and 0 cents. We don't need that in the data set and stuff like that. So this is actually more complicated than just grab the database and then go. It's get the database, go through it, clean it, check it for problems, check if people entered in weird things and stuff like that. So then you collect all your data, and then we get to the meat of it, or at least the thing that we think is the more fun part, which is build some network architecture, give it some training algorithm, and then see if it trains. And that's kind of like, it's kind of that simple, especially because the tools that we have now basically make it that simple, where it's like, define your network, give me data, and then type import TensorFlow, and then do TensorFlow.train or whatever it is, and then your network's trained. It almost is literally that simple. It's kind of scary because a lot of people just use Python for this. And I can explain the reasons for why they use Python, but the point is this part actually can be pretty easy to just feed it data and then hit run. The challenging part then after that is doing an analysis of your network. Is it performing well enough? Is it reaching the accuracy that we want? Is it minimizing the loss? Is the network making any like fundamental mistakes that you see that could be problematic? Is the network efficient enough? Like, is your network so big that it takes it 10 seconds to run every transaction through it? Because if you have to run 1 million transactions through it a day, then you like literally don't have the time in the day to process all of that information. So that's a problem. So you kind of ask these questions, and I'm sure there's plenty of other questions you could come up with. Is it biased in one direction or another? Is the data set actually good enough for it to get all of the different test cases and things like that? And if the answer is no, it's not good enough, then you got to go back, find a different learning algorithm, find a different network architecture, find a different whatever to make it. But let's assume it does work, because essentially what you would end up doing is just repeating, make a new network, train it. Is it good enough? No. Then make a new network, train it. Is it good enough? Is kind of what happens. So let's assume it works. You can then deploy it usually to some cloud system. And then you kind of continue to iterate on it, even while it's deployed. Because while it's deployed, you have this cool thing of you can also be collecting data because you're running all the data through it. So you might as well be collecting it and keeping that to train another network to see if that one can improve and things like that. So that would be kind of like a really kind of, it actually seems kind of simple, but that's because the meat and potatoes lies in between these two steps, the training the network and then analyzing it to make sure it runs well enough. The deploying it's actually kind of simple. The collecting data is also very challenging, but the idea of it is relatively simple, but the implementation of how you do that is kind of where the challenge lies. So here are a couple of things that I skipped over. This is by no means a comprehensive list. There are tons more things that I could go into. There's activation functions, which we kind of skipped over right at the beginning, supervised, unsupervised, semi-supervised, or reinforcement learning. There's spiking neural networks, which are their own problem. Recurrent neural networks, AI ethics, and then some tools like TensorFlow and PyTorch are all a bunch of random things that you could use. Well, these two are kind of the main two things people use for training their algorithms. So, yeah, that is everything I have. So I'm done boring you guys to tears. Hopefully I didn't bore you that much. But I'll make sure I drop a link to this in the chat. So
Just go ahead and drop a link to the slides in the ACM chat, probably.
Yes.
I'll make an announcement and post them on there too, so everyone can find them easy peasy. So
awesome.
Well, yeah, that was awesome, Joey. Thank you so much. That was fantastic. It was pretty cool learning about the ins and outs of the magical world of AI.
Awesome. Yeah, thank you so much.
No, thank you for coming out again. It was a treat. We have a question from Esteban. He says, why is Python a popular tool for this?
Okay, so that's an excellent question because people would think Python is a terrible choice for this because Python is slow, right? At least that's what we're always told. Yes. And it is slow. But, and this is kind of like pretty much everything is like, yes, but. What you use, these libraries like TensorFlow and PyTorch, the reason you can use them is because under the hood, they have been like brutally optimized. And I think a lot of it's written under the hood in C, because there's a connection between Python and C that you can make. And so what happens is when you write with Python, you can then import